we talk about the Cauchy-Riemann condition, and also we talk about the complex integration for the analytic function. It should be 0. That is a Cauchy integral. Now we would like to talk about how the Cauchy integral can be used to take the complex integrations. Let's look at here. Fg is an analytic function in whole domains. Then we would like to integrate another function. This is the analytic function, but we would like to we would create another function, this one. So this one is a singular at the z equal a. Okay, so this function is not analytical at this point, except at this point. This one is analytic, the other area. So we would like to concern the nearby this is singular point. So to testing this one, we defined a small segment contour delta c. That's this one. This one is a small contour around the singular point, and define the g minus a. Okay, g minus a is this vector. So g minus a vector is a magnitude. The radius is epsilon. Epsilon is the radius of this length. So epsilon is very small but constant, the whole contour. And the theta is the angle theta changing along the contour like this way, theta changing from 0 to 2 pi, but the epsilon is constant. Then we can define the dz. Okay, by taking dz as a constant a, so this is disappear, and the epsilon is constant, theta is variable, so it will give j will come out by taking differentiation. So epsilon j and e to the j theta d theta is the dz. So we define dz, so enter that one into here, and there is a single variable. You know, the epsilon is constant on this contour. We take the contour integrals in these directions, so theta will changing from 0 to 2 pi. Okay, and z is this one. Okay, z is a plus epsilon e to j theta. Okay, this plus this value will give the z, and g minus a is this one. So epsilon e to j theta, and dz is j epsilon e to j theta. Looks like, and this d theta will changing from 0 to 2 pi. So we have a very small radius epsilon. So we take the epsilon goes to 0. We would like to measure the result of that one. So that in that case, you know that exponential j theta and epsilon will cancel each other, and this one is a small enough if taking epsilon goes to 0. So it's a fa, and just a multiply of 2 pi. You know the theta changing from 0 to 2 pi. So j is remained here. J 2 pi times fa is the integral result of this one. Okay, so we take the integration of this one, and it's given 2 pi times j and fa. So what is this fa? We call this one is called the residue of this function. We defined this function fg over g minus a, but this function is singular at the g equal a. But taking integration over here, if this function is analytic, it should be 0, but it is not analytic at the g equal a point. So if we find out the residue of this one, we can integrate that one. Okay, so here shows how that one can be used. Assume that fg is analytic the whole domain, but we would like to measure this one. Okay, this one. At this moment, g0 is a singular point. Okay, and we would like to take integration over the contour like this one. It's a closed contour. But at this moment, g0 point is not analytic. Okay, fg over g minus g0 is not analytic at this point. So it is not 0. Okay, so how we can make it 0? This contour decomposed into two different components. Okay, one is this one is this contour. Okay, but when we meet this singular point, we can deep into these directions. and clockwise direction, rotate and come back out. Then entering and outcoming path cancelled each other, so it's a disappear. And this integration, clockwise integration, and adding the counterclockwise integration is added. Then that becomes the same as this one. By taking contour C0 like this path, so we exclude this singular point by taking this contour. By taking this contour, it seems like weird, but the entering and outgoing paths cancelled each other. There is some path that exists, but this integration doesn't include any the non-analytic area. So by taking integration of this one should be 0. Okay, because this function is analytic on this whole area, except this one. We didn't include this one. We excluded the path of this one. To equal this one, we have to add this part. That's this one. C1 contour taking these directions. But we know that that result are given like that. At here, the residue is fg0. So this integration are equals to 2 pi z times fg0. So we can take integration by use of residue theory. So this one is called residue. Okay, residue is defined 1 over 2 pi z, and taking closed contour integration fg over g minus a, g minus g0. Okay, this one is the how the Cauchy integral can be used to find out the complex integration. We take the integration of this one. So there is some singular point that exists here. Then that gives the residue value at here. The prerequisite is this one. Fg should be analytic one. Okay, and we call G0 is the pole. Okay, but what if there is another singular point that existed? There is a two poles that exist inside of the contour. Then how are we gonna do that? So this is that one. But integration is a linear one, so we can find out the sum of the residue at the G0 residue and G1 residue can be found from here, and multiply 2 pi will give the integration result. Okay, and how to find out the residue value? Look at here. So there is two different poles that exist here. The first one is G0. To find out the residue with respect to G0, then we can multiply this value to this integration value. That's this part. G minus G0 over Fg plus G plus G0, G minus G1. Okay, G minus G1 over F of G. Okay, this part is integrand of this one. Multiply this one and apply G approach to the G0. If you multiply this one will cancelled out. So apply this one will give f of G0 will come out. You know that G minus G0 is applied here. Then taking G goes to the G0, then this part will clear out. So only this part will remain. Similarly, we can multiply G minus G1 to the integrand, then this will cancel out this one product here. Taking G approach to the G1, then this one will cancel out, and that will give FG1. So this one, how we can find out the residue value of the function. Okay, next, what if we know that Fg is analytic, and G minus G0 over F of G, taking integration of for a given a closed contour will give residue value of this one. Then what if we take the derivative G0, okay, F prime over G0, okay, this one defined delta G0 is equals to 0, then delta G0 over F minus F. This is definition of this F prime of G. G0, delta G0 should be approached to the 0, and the delta G is over here. And we know that the f of g plus g0 are this one. Okay, from here, g0 should be g0 plus delta g. Okay, this part should be replace that one. That will give this result. Okay, fg over g minus g0 minus delta g and dg. And what about this one? This one is the same as that one. Okay, this is it. We have to take the same contour from here, so we can factor it. Okay, like that. And then we can make it simplify like this way. Then from here, we take the g goes to 0, and delta g will cancel out and take the limit. Then this goes to 0. Then it will give square of g minus g0 of f of g will give this value. What is the prime g0? Okay, that is double poles. In case of double pole, it will give this value. Okay, this means that any given closed contour, if fg is analytic and fg over minus g0, you would like to taking closed contour integration on this contour equals to 2 pi times residue. Okay, this one is always 2 pi times 2 pi j times fg0. So if what is should be f of g0. Okay, this is the integration for first order. What about this one? This here is g0. Okay, if g0 is a double pole, fg is analytic. fg is analytic. Okay, fc over g minus g0 square. So at this moment is a double pole. This will give 2 pi times j f prime g0. Okay, this is this result. From here, if pole is a double right here like that, then it will give f prime of g. What about the triple pole? In that case, it's a double prime and 2. And what about n plus 1? In that case, n factorial of nth derivative of f and evaluated g0. So we can integrate multiple pole cases by use of this one. That is summarized over here. Okay. Now consider some of the examples. First one, let's define contour like this one. The radius is just 2. Okay, that's the closed contour. It's a circle. And we would like to integrate this function, this complex function, on this closed contour. We can factor this one into this way. There is two different poles, minus j and j is the pole. That's this j for this pole and minus j for these poles. And to find out the integration result, we need to evaluate the residue of the j and the minus j. Okay, the residue j can be found multiply these terms, so this one will disappeared, and we insert j onto here. Then that gives a j plus 1 over minus 1 and minus 1. That gives this residue. And what about minus j residue? Minus j residue can be found by multiplying these terms, and that will cancel out for that. And g minus j is remained. The g square minus a. So at here we replace j with minus j. That's this residue value. then that it will give minus 1 minus j, this one, and minus j square will be minus 1, so minus 1 will be minus 2. By summing up, it's 0. So the integration of this one is equals to 0. The next example, now the contour is defined the unit circle. Okay, this is the contour to take integrations. Okay, this is the contour. Would like to integrations, and the complex function is 1 over g minus 3 and g plus 2. At this moment, there is two poles. One is a 3, another one is a minus 1.5. But at this moment, only these poles are inside of these circles. Okay, so we need to evaluate the residue value for this one. So multiply g plus 1.5, and this one will disappear, and g approach to minus 1.5, and g minus 3 over 1. Okay, then it will give a minus 0.5 and minus 3, and multiply 2 pi j will give the integration of that one. So we can find out the contour integration of this one by use of residue theory. Okay.